Okay, for inelastic collisions, all we had to worry about was adding up the momentum before and making sure it was the same as the total momentum in the end. Now, elastic collisions are a little more complicated because since they're bouncing apart, there is going to be two velocities in the beginning and two velocities in the end. But we do have two things going for us. Momentum still is conserved, but so is kinetic energy. And so, let's do one example here. We're going to have one mass. We're going to say that this is 10 kilograms. And it's going to be going at a velocity of 5 meters per second. Okay? Now it's going to collide with another ball that is also 10 kilograms, but it is not going anywhere. So this is 0 meters per second. Now when they collide, we're going to see that we have two of these, and they should have v1 and v2 velocities. They still have 10 kilograms each, but after they collide, they should each have their own velocity. Alright, and so what I do is, to begin with, I work on momentum, and then I work on kinetic energy, and you're actually going to end up with two equations and two variables. So when you work out momentum and kinetic energy, you're going to get two equations, one in each, and you have to plug them in the end to figure out the total velocities. So let's work on momentum here. On the left side here, our total momentum is only going to be with this right here, because that's the only one with movement. So it's going to have 50 momentum beforehand. Afterwards, though, we're going to have this momentum and this momentum. So for the first object, it'll be 10 times v1. The second object will also be 10 times, but v2. Alright, and then I also check to see if I can't simplify anything in my equation. One thing I notice is that everything is divisible by 10. So as long as I divide everything in the equation by 10, it's actually going to be simpler. It's going to be 5 equals v1 plus v2. Alright. Now, let's go over to kinetic energy. Now, the total kinetic energy is just going to just be with this one object that's going towards the other one. So it's going to be 1/2 mass times the velocity squared. But in the end, I should have two kinetic energies for the two objects, and we have to use 1/2 times the mass times the first velocity, and for the second object, 1/2 the mass times the second velocity. Okay, now this is kind of nice. In this case, we have a 1/2 in everything, which can cancel. We also have a 10 in everything, which can cancel. That's not always going to happen, but often you can, like on the left side, divide by the same number. So what we end up with here is 25 equals v1 squared plus v2 squared. Alright, so I have to combine these two equations. What I'm going to do here is I'm going to get v1 alone, and then I'm going to plug it into the v1 over here. So I'm going to subtract v2 to both sides. That'd be 5 minus v2 equals v1. Now instead of writing v1 on the other side, I'm going to write this 5 minus v2. I'm going to substitute. So now this is where I start combining. 25 equals, and instead of v1 here, I'm going to write v minus 5 minus v2 all squared plus v2 squared. Okay, now I have to scroll down here a bit. Now, when I substitute in, I actually have one equation with one unknown. So I just have to simplify. First of all, I'm going to FOIL this out. This is actually the same as 5 minus v2 times 5 minus v2 plus v2 squared. So I have to first, outside, insides, and last there. After you FOIL this out, you should get 25 minus 10v2 plus v2 squared plus v2 squared. Okay, keep going here. you have 25 minus 10v2 plus 2v2 squared. And I can actually subtract 25 from both sides. So I have this all equal to 0. I have 2v2 squared minus 10v2. Now, since this is equal to 0, I can pull out a common factor here, which 2v2's can go into both. And I would end up with this. Now, the answer's here. v2, if that is 0, this whole thing is 0 and the equation works. But this doesn't make sense to us because originally we said that this second object should be having some momentum. The total velocity can't disappear. So this, when is v2 minus 5, 0? That is going to be our answer. Alright. So now if you think about this, what this means is that the original object hit our stationary object and transferred all of its momentum, all of its velocity kind of, to the second object. So if v2 is 5, we can go back to our equation up here. 5 minus 5 equals v1. So v1 is going at 0 meters per second. So the reason this makes sense is if you think about billiards, a professional player can do this almost exactly. He can, without spin, hit the cue ball into another ball, and if he does it perfectly, the second ball gets knocked away from the cue, and the cue ball just stays stationary. And so if you have the same exact mass in both objects, actually all of the momentum will be switched over. So this was an example, and it's special because the masses are all the same. All the velocity gets switched over. But in the next example I'm going to show you, we're going to have different masses, which means there are going to be different velocities in the end.